So welcome everybody. For those who don't know Miguel, Miguel González-Fierro is a senior data scientist at Microsoft UK, where his job consists of helping customers leverage their processing using big data and machine learning. He was previously CEO and founder of Samia Technologies, a company that created a visual search engine for fashion items, allowing users to find products using images instead of words. And he was also the founder of the Robotics Society of Universidad Carlos III, which developed different projects relating to UAVs, mobile robots, small humanoid competitions, and 3D printers. And there's some videos, I believe, of those. Miguel, maybe you could share some of those. They're pretty interesting to watch. Miguel also worked as a robotics scientist at the Universidad Carlos III of Madrid, UC3M, and King's College London, where his research focused on learning from demonstration, reinforcement learning, computer vision, and dynamic control of humanoid robots. Miguel is an electrical engineer at UC3M, PhD in robotics in collaboration with King's College London, and he also graduated by MIT Sloan School of Management. So quite the background. Miguel, super excited for this and very grateful. I know you're joining from overseas, and we really appreciate it. So I won't hold everybody up. I'm going to let you get to it, and I'll make you host, and everybody enjoy. Okay, thank you so much.
Awesome, thank you. Good morning, guys. Yeah, super excited to be here. I will have loved really to be in Toronto, but you know, these times are quite difficult, right? Let me share my screen. Okay, so this is a talk that is based on a work of several people. Here is the list of everyone, and this is something that we presented at KDD. And the idea is that we wanted to kind of help somehow in this COVID situation, and we came up with a way of recommending papers related to COVID. And for that, we use a recommendation system that uses a knowledge graph and also a knowledge graph done by Microsoft that is called Microsoft Academic Graph. And also we explain how this can be operationalized. So this is a little bit sad, and sorry to lower the mood, but to the left, I have the stats that we presented, that they were presented at KDD. And that's 23 million cases and 800,000 deaths by COVID. Today, I look at it this morning, and it's 44 million cases and 1.3 million deaths. I just want to stop a second to reflect on how crazy this is. Like I was, sometimes when you see the number 1.3 million or 800K, it's just a number, right? You know, the way I think is, so I'm from Spain. In Spain, typically we like what we call football, right? You guys call it soccer. But if you've been in a big stadium, so one of the biggest stadiums in Spain is Real Madrid football stadium, right? So that stadium is 80,000 people. So if you've been in a stadium like that, you'll see how crazy is 80,000 people. So 10 times more or 15 times more that number plus families is absolutely crazy. Okay, so yeah, just 1-2 minutes to kind of reflect on this. Okay. So yeah, first of all, I just shared the link of the code. In the past, some people wanted to follow the steps while I'm talking. You know, feel free to do it, or otherwise just listen and talk. All the content is shared, so you can guys take a look and reuse it. basically the idea is what I just mentioned, right? Like try to recommend papers based on a data set of related papers. And yeah, this is the link to where all the code can be found, and I also put it on the chat, so in case people wants to follow this, just feel free. This is here basically. Here basically is the code. This is basically based on a repository that we are doing at Microsoft called Microsoft Recommenders. The data set is kind of cleaned for everyone, so it's easy to do. We need to install the compiler and also create a conda environment. There is a CPU and GPU environment. I recommend to use a GPU environment because obviously it's faster, but with the CPU should work the same. And basically, once you install the conda environment, just start running the notebooks, and hopefully everything should work. Okay. Okay. So first thing is the data set that we used. First, we combine two components. The first is the core 19 dataset, which is a dataset of related articles about COVID. And at the same time, we use the Microsoft Academic Graph, which is a large graph, knowledge graph of academic research. This is something that it can be queried. This data set is done by many people. So Microsoft Research, AL2, Georgetown University, and others, with obviously the objective to facilitate the fight of COVID-19. The idea is to use different publications and try to come up with a data set so people can do machine learning on it or any other task. Another thing that I didn't say is that these slides also are going to be shared. So at the end of the talk, I'll share the link, so people want to get the links, they're going to be provided. And Microsoft Academic Graph, this is done by Microsoft Research and using a multitude of scientific research papers. It started a long time ago, 2014. And the idea is to have a graph system of publications, authors, topics, conference journals, and institutions. Right. So the idea is to create this massive graph that people can query with the objective to facilitate research. And the idea we propose is to mix both data sets and see how a recommendation system can benefit from a knowledge graph capabilities. The way, if anyone wants to replicate this, basically there are kind of two steps, right? So the first step is, so first get the core 19 data, get the API keys and get access to MAG, and with a PySpark script get the subgraph. The subgraph of core 19 MAG is basically all the knowledge graph components related to the core 19 papers, right? and then the other way is kind of the other way around, like so basically you take the core 19 papers, you get the IDs, and then you map the IDs through the API and just get the subgraph using that API. So these are the two ways of doing this. For the tutorial, basically this is already done. So one of the first steps is downloading the data. Here, but basically that's the step that we need. Okay. So now the next thing is we're going to do several things in this tutorial. First is more like data analytics and analysis. And the second thing is to do our recommendation system. So the idea is to understand the this data set with the help of a knowledge graph. What kind of things we can get? Trends, where these papers are being published, the geolocation, the kind of the size of the team publishing this, and even the topic distributions. And this is something that it is also in one of the in this in one of the notebooks, the first notebook. Okay. Yeah. So basically, this is just a comparison of how does the core 19 subgraph.
Okay, so I don't know if you can see my screen.
Sorry.
Oh, sure.
Sorry. Yeah, so this is kind of for you guys to compare the difference between the subgraph and the graph. So a number of nodes, 600K, and edges 2 million versus 480 million nodes and 4 billion edges, right? So it's a very, very, very small part of the overall graph, right? And yeah, so this is just a review on some things that some analytics that we can get, like what are the domains, medicine, psychology, well, medicine and biology obviously are the biggest ones, and then we have others. Computer science is a very small one, so people in our field, you know, are doing a small contribution. And then we can also see the subdomains, right? In terms of the place where this was published, medRxiv, +1 Journal of Virology. I honestly, I'm not familiar with any of these publications because this is not my field, but well. And well, this is interesting, right? Like co-research coming from the past 20 years. Well, so you see that this is growing steadily, and suddenly here we have a massive peak here. Well, this is another thing that we can reflect, right? Like, yeah, like when people are in danger, you know, everybody starts funding scientists. So maybe we should have been smarter and try to predict that something like this can happen, and maybe, you know, invest a little bit more on these kind of things, right? And another thing is the team size distribution, like a majority of small teams, like 2, 4, 6, and 8 is a majority. And now the kind of application of knowledge graph in recommendation. So now this is more, so we've seen the part of analytics that basically, well, this is the graph. I don't going to spend a lot of time on this because this is kind of, easy to do, just analytics, right? But basically here you have all the code if you want to take a look. Now, the next idea is how we can leverage this knowledge graph information.
Yeah. Sorry, it's Dave here. Can you just make me co-host? I think there's some people in the waiting room. I just want to let them in.
Yes.
So I think if you go to participants in the bottom, click on that.
Okay. This. What? How can I make you host?
Okay. So if you can find my name, I think even if you click on perhaps the chat box. Yeah.
Yeah. And now, make host.
Yes.
Do you want to change host? Yes.
Even the co-host is fine. Yeah, that's fine. Sorry to interrupt. That's great. Thanks, Miguel.
Okay. Yes. Okay. No worries. No worries. Yeah. So in the code that we shared, there are actually two networks. One is a DKN, knowledge-aware deep recommendation model, which is the network that I'm going to go a little bit deeper. The other one is light GCN, which is another network that I'm going to talk about it today. But this is something that is the code is there, so you can take a look. Yeah, the tasks that we are going to show are the author to paper recommendation. So based on the citation history and the specifics of the author, we are going to recommend papers. And then a paper to paper recommendation, which is, well, similar papers. I wish I would have this on my PhD, because I'm sure this is something that I could have benefit from, right? So this is a representation, a visualization of the graph. So we took just a small number of entities, and this is how it is done. The code is here. You can take a look. And obviously, the one interesting feature of knowledge graph is that they show relationships. This is something that is not easy to perceive on a typical tabular database. And this is the Microsoft Recommender Repository. Is a repository with examples and best practices around recommendation systems. I think so far is the most popular repository around recommendation. And here's where we host the code, and we have a large number of algorithms. There has been a lot of contributions from Microsoft Research, but also from other parts of Microsoft and also outside Microsoft. So it's completely open source, and people can take a look. And it's not only algorithms, machine learning algorithms. It is kind of the full life cycle of recommendation systems. So data prep, machine learning training, machine learning evaluation, and even deployment and operationalization. So this network, the reference is at the end. Basically, the original idea was for news recommendation. So it was, the original research was done for MSN News, which is one page that we have on Microsoft for news, right? And the idea is to understand the click history of people and mix that with a knowledge graph. The knowledge graph is used to enrich the features. And the task is whether the user will click on is the next click prediction, right? Like whether the user was going to click on the news or not. And this is the architecture of the network. So we have a candidate news, and for this we compute something called a knowledge-aware CNN, which is a convolutional network structure that includes the knowledge graph information, and it has it is composed as a matrix. So then on top of that we can do convolutions. If you guys are familiar with char CNN, on all the research around NLP with convolutional networks, the idea is kind of similar. So on the one hand, we have the candidate news, and then we have the history of news, right? And on top of that, the authors created an attention network, and then at the end we have the user embeddings and the candidate news embeddings, and the click rate prediction is just multiplication, right? The way the knowledge graph is done is based on context related entities. So imagine that you want to find the context related entities of Fight Club. So you have like first level of connections would be something like the country is United States, actor is Brad Pitt, Jern nominated to the Oscar, right? So this kind of is kind of the first level, right? And then second level will be much higher, like, so Brad Pitt, for example, is a male, and so he's from United States, and another actor from United States is Leonardo DiCaprio, right? So this is how you can create this. As you can imagine, the biggest the circle, the number of relationships can grow exponentially. So it's not there needs to be a way to filter that. And this is kind of how the knowledge-aware CNN is created. So there are like 3 channels for this. First of all is some word embeddings. These word embeddings are done with Glove. Glove is an NLP algorithm to generate embeddings that is based on word co-occurrence. But as you can imagine here, we can remove Glove and put any other embedding generator like BERT, for example, some of the most modern BERT, or even something lighter like the fast text embedding generators, for example. And basically this is how it is done, right? So we have n words, so from 1 to 7 in this case, and then we have a dimension D, which is the second dimension of the embedding. So basically this the word embeddings basically is creating a matrix here, you see. And then basically we replicate this for the entity embedding. So we get entities for this, like in this case would be Galaxy Note 20. These are the entities, right? And we compute embeddings as well. And then the third channel is the transform context embeddings, which basically is we go to the knowledge graph, we find the contextual entities, which is first degree of relations, and then we compute same thing for these context embeddings, right? And then on top of that, there is a convolution, and then finally pooling. So this is how it's computed. So now we're going to go to the notebook before we go to the to the final part. So I'm going to go a little bit fast on this, just because we don't have a lot of time. But I wanted to show you how the notebooks look like. So for the first notebook is data prep. These are actually not the original names, just because. So here you have the original names. Data prep, embeddings, run DKN, and then run DKN item to item. And then this is the one that we're going to talk, the LITCM. So for DKN, the format is an ID, the words for the name, and the entities. So this will be a quick example. One whole approach is Southeast Asia region, opportunities and challenges, right? So title words can be something like this, and then the entities will be something like this, right? So that's kind of the input, and basically what we need to do is to get the original paper information and transform that into this format. And so we created some functions that allows you to do that. So basically here is just taking the word embeddings, so indexes of the words and the entities, right? Then we need to generate the user-related files. So this is for user to paper recommendations. So we need to collect the cited papers and arrange them. And in order for the recommendation is stated like given a user's citation history, what will be the next paper this person will cite, right? So we need to create the training validation and test files for the DKN, and so this is the format. So label, user ID, candidate news, impression ID, and so label is click or not click, basically. And then also the user history file. So it's just a user and then the IDs of the news. So at the end, DKN is a binary classification problem. So this is how the splits are created, and then we need to do the same thing for item to item recommendation. So the idea is that given a paper, we can recommend a list of related papers. And this is just a supervised learning approach. So we have instance of paper A, paper B label, where label 1 means that they are related, and otherwise is 0. So this is something that, in fact, this is this approach is something that we did for this specific publication. The way we do is paper A and B overlap in the list. Paper A and B are co-cited, and paper A and B are published in 12 months by the same author. Okay. So kind of the same idea. So generate the splits, and that's the data prep. So once we have the data, the next thing is to generate the embeddings. So here we have word2vec. So I said that we use Glove, but in fact, in another part of the code, we're using Glove, but word2vec is something that also can be done. And as I said, it can be it can be used by using fasttext or even model BERT as well. Yeah, so this is how we get embeddings, and here we need to compute the knowledge graph embeddings. And to compute the knowledge graph embeddings, basically we use a library that is called trans-E. And the idea of trans-E is that it is a function that basically takes the origin and connection of the graph has to be equal to the end. Let me see if I have here the, yeah. So here I have the original paper just to, so this is kind of how it is done, right? So H plus R, so head and relationship needs to be equal to tail. And this is how it is computed. So it's quite simple. There are other different forms of this, and in fact, the library that we mentioned here actually has all of them, but the one that we chose is trans-E. So these are the embeddings for the knowledge graph that are computed, and at the end we have the entity embeddings, word embeddings, and the knowledge graph embeddings. So the DKN model basically, so yeah, this is kind of the same. The format that I mentioned, so label, user ID, candidate, news, and impression, plus a user history file, and then all the embeddings, all the embeddings for a document, and then word embeddings, entity embeddings, and context embeddings. So here are all the paths. There is here the list of hyperparameters, and this is the network. So the network just this is the original kind of evaluation with no training, let's say, and you see that the AUC is 50%, which is random chance, and then we start training, and we see that the AUC and other metrics have gone better. The code that we have allows us to generate embeddings for the features. So it's for each news compute embeddings, and this is something that can be used for operationalization. This is just another experiment. The code that is given in the repository basically uses kind of a partial version of all the data set, just because if not, it will take a long time to compute. But we can do the same with a full data set, and then, well, this will take some more time. And you see here the results. So this is, I compute this on Friday, I think. This is kind of the result, right? So it's quite similar. Group AUC, group C. This is the comparison DKN and DKN removing the knowledge embeddings. And this is the comparison with like GCN, which is worse. And here we basically compute the item-to-item recommendation. So the idea is to compute the embeddings and then do just a simple cosine similarity between them and measure whether they are related or not related, right? Yeah, so here is kind of visualization on the code. I didn't talk about how this is included, but basically this is done in terms of flow, and basically there are like two main components. One is the iterator, like the data is fed into the GPU in batches, and then we have the actual network. So in a similar way that we have DKN item to item iteration and DKN item to item, we have DKN iterator, which is the previous example that we've seen, and DKN. We, in order for us to compute this, we need to do a negative sampling. In this case, we chose 9. And this was also how it was trained. And yeah, so here we can see the model, and these are kind of the results. Okay. So yeah, as I said, all the code is there, and you can take a look. Yeah, I think I'm quite on time. Now I'm going to talk on, okay, so once we have the once we have this knowledge graph recommender, how this can be put in production. So talk a little bit about graph databases and how very quickly how they are different to typical tabular databases, and how this is done in how this is operationalized in real time or other structures. So very quickly, there is a large market of knowledge graph initiatives. So companies like Microsoft, Alibaba, Amazon, eBay, so they all have knowledge graphs. Some of them are private, some of them are open source. So Microsoft, for example, this one for Microsoft Academic Graph is open source, and there are others like Wikidata. In recommended repository, we have an example of a knowledge graph computation using Wikidata graph. DBpedia is another one. And then we have other areas like finance. So in finance is quite popular, especially Ant they have done a lot of work and even research on that area. And even we have graphs related to networks like Facebook or Airbnb or even LinkedIn. Another interesting thing is that, well, we are seeing here the application of knowledge graph into recommendation systems, but there are a huge number of applications that we can use with knowledge graph: customer experience, target market campaign, digital assistance, fraud detection is a quite big one in the finance industry, and then search engine or segmentation as well. So here, a list of some applications. The one I know most is Satori, who is an internal knowledge graph service for Microsoft. Also, Wikipedia here is open source. And then there are others, the graph search from Facebook, Google, LinkedIn, even Amazon, a good number of those. And this is a quick example on how a graph database is different to a typical data set. So database. So let's say we want to know the name of a person that works in a department, right? If we want to do this query in SQL, so it will be this one. So select name from person, left join person department, left join department, where department is IT department, right? So basically, we need to do several joins to find something like that. In a graph database, this is quite easier. So it's match a person that works at department where the name of the department is IT department. So it's something quite, it's faster. I would say it's not that popular just because people, I would say there are less applications of graph information than in typical tabular databases, but still is something that I would say with more and more research on knowledge graph, maybe we see more graph databases. And there are several languages. The one that I'm familiar with is Gremlin, which is the one that we have in Azure Cosmos DB. And then there are other Cypher, Neo4j, RaceGraph, and then SparkQL that is like, trying to imitate SQL for these other platforms. And then just to finalize the real-time scoring in recommendations. So we propose here 3 ways that, at least in our experience, we've seen commonly. So the first one is a lookup in a pre-score, so based on pre-score recommendation results. The other one is a real-time scoring based on approximate similarity matching. This is kind of the typical way that people do search engines, right? And then there are some tricks that some companies uses for operationalizing this kind of recommendation systems. So this is the real-time lookup of pre-score recommendations. So the first step is to do the training. This step is typically done offline. So you taking the user items and interactions, they are stored in some storage, and using some kind of compute, we compute the machine learning model, kind of the way we did in the tutorial, and then we score for each user. We'll score a top K recommendation, right? This top K typically is bigger than the number of items that you want to serve, because sometimes there are some business rules that you may want to apply, right? So at the end, you have a matrix of users time number of items, which are the top recommendation. This is stored in some database. Here we use Cosmos DB, and then on top of that, we use a Kubernetes cluster that allows to do the lookup in real time, right? The benefit of this is that this is very, very fast. As you can imagine, you can even do it faster with a Redis database. So it's a cache database. The problem is that this is obviously not real time. You need, this is something that typically is trained every day. So every night you compute this and update the new recommendations, and that's what you serve. Okay. The other way is real-time scoring based on approximate similarity matching. This is, for example, a very nice case for the item-to-item similarity example that we put earlier. So the first step is to compute the embeddings, and then a similarity index is built. There are several methods, KD trees, LSH, right? And this similarity matrix, similarity index, depending on the library, is typically like an internal, so it's a model that is actually kind of a database in memory, right? So this is something that you can directly operationalize in a machine. And then on top, you can use AKS to handle all the requests. And then the way this is served is given a user item query. The first step is to compute the embedding, the query embedding, and then using the approximate similarity model, find the most similar embeddings. And this is done in real time. Okay. And then the output is the IDs of the similar objects, which is what you send to the client. And then finally, there are a lot of papers on how different methods of operationalizing systems like this. Modern recommendation systems are based on deep learning. The one that I showed is based on deep learning, so obviously uses GPU. There is a nice paper from Alibaba explaining how they do their infrastructure on for the recommender that they have. So they do request batching. So basically merges different requests to do the inference in the GPU and do a better utilization of the GPU. Then GPU memory optimization. Again, with the objective to improve the GPU utilization, and concurrent kernel computation to allow to compute to make the computations in several kernels at the same time. So here's a paper, and it's quite interesting to read. Yeah, I think that's all. There are kind of 10 minutes for questions. And yeah, so just a summary, try to understand how knowledge graph technology look like, an analysis of the core 19 data set and the Microsoft Academic Graph service, understanding of DKN, this deep knowledge aware recommender, and a brief understanding on operationalization, on how these models can be operationalized. These are the references. As I said, I'll copy the link of the presentation, and yeah, I think that's all.
Thank you so much, Miguel. I'll open this up for those who may have some questions here, and I see Max in the chat. I'll let you take those questions as they come in.
Yeah. So, yeah. Okay. Yeah, so MAG is Microsoft Academic Graph. Oh yeah, somebody replied here. Okay. You able to share the notebooks as well? Yes. So the code is here. A traditional recommender. Yeah, so that's a good question. Here in our research, we didn't compare another recommender. Yeah, I think it's here. You still see my screen, right? Oh, sorry. Sorry. Yeah. This is one recommender that doesn't have knowledge graph, and we see that the performance is not the same. And DKN actually is DKN minus is the recommender that doesn't have the knowledge graph entities added. So it's just word and word-based entities and so word embeddings and entity embeddings. And we see that this is poor. And then in the paper, so yeah, so here they have some comparison. Wide and deep, for example, this is a well-known algorithm by Google. So one of the first used on YouTube. LibFM, DeepFM, also another one. I don't know if they use. Oh yeah. So this here is the comparison, and yeah, basically we see that the use of the knowledge graph enrich the entities and the embedding. So this is something that is typically should work better. Obviously, another thing is attention. So this is since this is an NLP problem as well, right? In the case of the paper, they are using the title of the news, but we can also have the content. The problem with that, obviously, it will be much more expensive in time, but using attention is quite important. Maybe to get. So yeah, the word-to-get glove fast text matter in the performance. It matters in the metrics, not the performance in terms of computation, right? So it's more like basically with word-to-get glove and fast text, or even if we want BERT, basically we are creating better embeddings, right? And does the vector get updated? No, basically this is kind of the input, right? And based on this input, we construct the knowledge aware CNN, right? So this is kind of the first the input layer, and then on top of that you can start doing the convolutions, right? So word embeddings are the keywords. So no, a word embedding is a representation of the word. So let me see if I can show something here. Yeah. So yeah. So basically, what we want is we want to have a compressed representation of the words, right? And what we do is there are several algorithms like word-to-get glove, fast text, that basically takes the text that is it can be any kind of text. It converts this into, for each sentence, it converts this into a fixed number of embeddings. So this is the D dimension that I showed here. This is the D dimension, and basically this embeddings, this is always fixed, right? And there are two important things. So first is that we are doing a a transformation between two spaces, the workspace and the embedding space. And also these embeddings are fixed. And since they are fixed, it is kind of easy to put this into a fixed matrix. And then on top of this fixed matrix, we can do convolutions or any other operation, right? So you mean so can you quickly review how the training labels are constructed and the dimensions? This is something that is in the code, and it's not quite easy to do, to explain quickly, but just to tell you what this is. So then paper content. So here we can go to let me see. Yeah, here. Yeah, so this is kind of the main function. Well, one of the main functions, and basically what we need to do is, you know, start understanding all the different parts of the text. One kind of difficulty is that this is not the code that we have here is not very general. So this code has been adapted to the specificity of the problem that we have, which is we want to recommend papers, academic papers. And obviously, there are several components that are related to this paper, like field study, category, right? But at the end, the idea is that, yeah. So the idea is that we need to take all the input information, transform that into embeddings, so word embeddings, entity embeddings, and then link the related entities using the knowledge graph, and also compute the embeddings. And these are the embeddings that we will use in as the input as the knowledge CNN, as the KCNN. What's your favorite graph, database, and why? I honestly don't have that much experience to tell you, hey, you know, this is a really good one versus the other ones. So in Microsoft we use Azure Cosmos DB, and basically this graph database is one that uses a Gremlin, which is the language that we use, and is quite nice. I don't have enough information for, you know, to use the other ones. So yeah. Any other question?
Yes, thanks, Miguel. This is fantastic. I really appreciate you taking the time, and it's 10 a.m. on the dot, so I guess we can wrap it up.
Yeah. I have the link to the slides. Do do you want me to share here in the chat, or should I send it to you?
Yeah,
Or
you could share it in the chat, and then if you could send it to me as well, I'll make sure everybody has it afterwards. And then
okay,
Ting had one question there, if you're able to answer that as well.
Training labels. Oh yeah, the ground truth. Yeah, so this is here in this case, we kind of needed to create our own ground truth, right? And so is given the user citation history, we compute what are the previous papers that this person cited, and this is kind of the history, right? And then these are kind of positive labels, and then we had to compute negative labels as well, right? So what are the papers that this person didn't cite, right? And that's how we create the labels. And then this is what is fed to the network, and then we compute the new predictions. Cool. Okay, thank you for. Sorry, I don't know if I shared this privately. Sorry, give me a second, because sorry. I think, can everyone? I just share everything to so the slides to everyone. I just shared to a person.
Yes, we got that, Miguel. Thank you. It's just in the chat there now.
Okay.
Great. Thank you so much, Miguel, and thank you everybody for joining. We still have some more workshops today and tomorrow, and then on the conference platform on Hopin, we'll kick things off on Wednesday and Thursday. So look forward to seeing everybody there. And thank you again, Miguel.
Okay, thank you everyone.